I'm not sure why it said it's private, cannot be public, the live on YouTube. Still figure out. I'm not sure why it said it's private.
I don't know. We can start a few minutes later. I think people are not here yet.
Yeah, for sure. Max, I think we can start now because some people are waiting on YouTube.
Oh, okay. That sounds good. Okay. Can everyone see that okay? All right. Okay. Should we start?
Yes, maybe
Yeah.
Max, you can introduce yourself to our audience first.
Yeah. Okay. Hi everyone. This is welcome to the USACO January gold level live solution session. So I'm Max. I guess about myself, I'm an instructor at XCamp. Some credentials, I was an ISPC World Finalist and a Codeforce Grandmaster, and I'm currently in charge of teaching the 602 level class at a XCamp. And I'll be presenting us a solution today. Yeah, so these are the three problems we'll be looking at today. It's from this just most recent contest. So Walking in Manhattan, Calculacy, and Nap Source. So I actually want to go ahead and share my whiteboard now, so I can first talk through how to solve each problem step by step, and then we can look at the knowledge required for these afterwards. So let me go ahead and switch to sharing my whiteboard. Okay, hope everyone can see that. Yeah, so let's begin with the first problem. So the first problem was a competency. So this is problem one. And the setup goes as follows. So we have a bunch of cows and we have a bunch of roads. So these roads are going to be they exist in a 2D plane. So they're either going to be like horizontal lines, they run infinitely horizontally, or they run infinitely vertically. So there'll be some lines like this. And there are a total of I believe there are a total of n less than 2 times 10 to the 5 lines. Hmm. Oh, I think my computer froze. Okay.
Oh, sorry, everyone. Let's wait for Max.
Yeah, okay. Sorry for technical difficulties, everyone. My computer crashed, so I had to restart it. Yeah. Um, yeah, okay. So this is where we were before.
1 second. Can everyone hear me?
Okay, cool. Yeah. So I was in the middle of explaining the setup for the set first problem, right? Yeah. So we have n less than equal to 2 times 10 to the 5 rows. So these are rows that run vertically or horizontally. And now we have to answer q less than equal to 2 times 10 to the 5 queries. And here's how, and it goes something like this. Um, yeah, it really crashed.
Teacher Max said he will join with his laptop. Sorry, everyone. Let's wait for a little bit.
Okay, can you hear me now? Hello? Okay, there we go. Oh my goodness, okay. Now if it crashes again, if it crashed on my laptop, then it was just not meant to be. But yeah, I'm on my laptop now. So all right, 275 rows, 275 queries. We want to, and what does a query look like? A query looks like we have a cow that starts at some location, and the cow is going to be moving, moving, moving. It's gonna move until it hits, like, say, a intersection at so the way it works is that when it hits an intersection, it will turn, it would continue moving either north or east depending on if it hits it at an odd time. So if it hits it at an odd time, then it will start moving, then it will continue moving to the right. And if it hits at an even time, it will continue moving up. So yeah. Okay, and so now the question is basically you have a bunch of queries of the form X, Y, and D, which tells you that some cow starts at position X, Y, and there was a move for D seconds. You know, they're gonna keep moving. At some point, they might hit this intersection at an even times, start switching, moving to the at odd times. They start switching over to moving to the right, and then they kind of just follow this path. And we want to know where do they end up after D seconds. Okay, so that is the statement. It is a bit of an overwhelming premise when you first look at this because you think I think the usual techniques for analyzing these problems don't quite work. If you try to think about it as a graph, you quickly realize there are up to n squared possible nodes because every intersection of like two different roads could be considered a vertex in this graph. So just even like thinking of it in this way is already too inefficient. So so kind of like a hint already to how we can possibly solve this is that we have to consider these as two independent parts, as like the x direction and the y direction. If we have to like couple these two parts together, there's absolutely no way we could hope to solve this in time. And so the key observation for this problem, which is quite interesting, is that it actually is like the movement in the x and y direction actually are kind of independent. And so they're not exactly independent, but they kind of are. And let me explain what I mean by that. So let's say we're a cow, we're moving to the right, and let's say that at these particular times, so at these particular intersections, we will switch from moving to the right to moving up instead, because we hit each of these at an odd time. Or I always forget, I forget if it's odd or even for moving up. We hit these at an even time. Yeah. So we hit each of these time point positions at an even time. And then if we hit each of these at an even time, then what happens is we will hit these at an even time. We will then move like, perhaps we will move like up some amount of time. But notice that the next time we switch from moving up to moving to the right will exactly be at an odd time. Right? Because that is exactly when we switch from moving up to moving right. So it's always that whenever it is an odd time at an intersection, we are moving to the right, and when it is an even time, we are moving up. Irregardless of like whatever we are doing, however much we move to this direction. What I mean, so like it's like when we hit this intersection at an even time, we'll switch to moving up. After some amount of time, we'll switch back to moving to the right. But it is guaranteed that it's the same cadence. We will again hit this intersection at an even time and then start moving up. It is never possible that like we move like some amounts going up and we end up in a situation where we're moving to the right and we hit this at an odd time. That is not possible because we always switch the directions on the exact same parity. And so let me say that means that like it's always going to be the same like positions or the same sets of positions of time where the same sets of like positions or the same sets of intersections where we switch from moving to the right to moving up. And the same argument can be made for moving up versus moving right, right? I could draw a similar diagram to show that the positions where we switch from moving up to moving right are always going to be the same positions, which is exactly when when the time becomes odd. I received a request to quickly recap the statement again. I guess the statement in short is that we have a bunch of roads that are either a bunch of rows that are either infinite horizontal or infinite vertical lines. And now we want to answer like Q queries where some cow starts at some position and it moves along these roads, and then when it hits the intersection, it will move to the right. If it hits it at an even time, and it will, or sorry, if it hits it at an odd time, and it will move up when it hits it at an even time. So those are the, and then we want to know like answer Q queries of like if a cow starts at some position and moves for D seconds, where do they end up? Yeah, so this is a pretty key observation because this tells us that like it's always going to be the same cadences, the same like sets of positions where the same intersection like points where we switch from moving to the right to moving up. And so what does that mean? Now now with that in mind, let's consider this. So our path is going to be that we move to the right, they move up, they move right, move up, move right, move up, right? We're gonna repeat that a few times. And so let's binary search on how many times we move right / up. So like this is like 1 step, 2 steps, 3 steps. Let's binary search on the number of steps. So let's binary search on the number of steps. And when we binary search, and then when we binary search the number of steps, let's just decide, or let's figure out. Okay, so what is that? Once we fix the number of steps, because of this analysis, we immediately know like where we're going to be at which points we're going to be moving up. So we're going to move up like here, we're going to move up here, and we're going to move up here, right? And so we can first accumulate all the distance that we move in the x direction. And then because we move up, and because we know we move up here, here, and here, we can also independently calculate like how much we will move up in the move in the y direction. So in the y direction is going to be a similar diagram where C might be moving up, and there are up to the cow moving up, and there are up to 3 positions or 3 rows where they switch from moving up to moving right. And we will also accumulate the total distance of this. And then we would just take the sum of the amount of the amount we move in the x plus the sum of the amount we move in the y and check if it is less than or equal to d. And if it is, then this many steps is valid, and we try to find the larger steps. We're trying to find the maximum number of steps we could take while we still take the total distance we move is less than or equal to d. And if we are able to do this computation, then we just find the maximum number of steps, and then we might have to also take an additional like move some amount to the right or to the up, which we can just simulate at the end or just manually check at the end. Do we need and I think someone in the chat asked if we need a prefix sums for this. I think it's even simpler than that. I think you just check like you can have a list of all the coordinates of where the intersections are, and we just binary search in that list. So we binary search for where the cow initially is, and then if we move 3 steps, it's just this x coordinate minus where the cow currently is. Yeah, and so to recap the total solution then is actually ends up being like a fairly short. It's just that for each query we answer each query independently. We just binary search on the number of steps we take, and we independently figure out how much we move in the x direction if we take that many steps, and how much we move in the y direction if we take that many steps. Because we know that regardless of the x or the y, it's always going to be the same like positions that we hit for that many steps. And so we just calculate that, check if less equal to d, binary search for the maximum number of steps for which that is true, and then do the extra like casework at the beginning and end for like, because at the very beginning you might not start an intersection, so you have to first like simulate up to the first intersection, and at the end you might still move like a little bit extra tail end. So you just need to do that extra casework at the beginning and end. And this will give us we have O of n pre-computation, just reading in the input. Actually, it might be n log n because we have to sort it. And then so say n log n because you have to sort the x and y arrays. And then for each query, it's going to be answer log n, so it's q log n. So the total complexity is n plus q log n. And that's going to be fast enough to solve the full constraints for this problem. All right, so any questions on the first problem of the contest? Cool. So I'm going to present the second one now. Let's present the second problem, which is it's a problem called competency. So this one has a bit of an involved setup. So the setup is we have there are n cows in a row. There are n less than 10 to the 9 cows, and each cow has some competency, technically competency, but I'll just write competency, ranging, which is one integer from 1 to c, where c is up to 10 to the, at most 10 to the 4. C is some input parameter. And now we want to know, so these cows are going to stand in a row. So the cows are going to be like A1, A2, A3. It's going to be some sequence where each of the A's is just the competency of each cow. So it's like basically you have an array of each, where each value, so 1 to C. And this array needs to satisfy a few constraints. I'm going to use C instead of A because there's a different A in the problem statement. So, okay. So now there are a Q constraints that we must respect. There are Q less than equal to 100 constraints. And what do these constraints look like? Well, each constraint is going to be some pair A comma H. And what it says is that all of 1 through A, so the first A cows in the array, all of these cows, out of all of these cows, H is the first cow to the right that is strictly greater. So to give an example, let's suppose that position A and position H are here and here, and we have some cows in between with like scores of like 1, 5, 2, and 3. And now this H means that the first position where something is strictly greater than anything in this prefix is right here. And so that means a possible array for which this works is like if we have a 6 right here, that is strictly greater than anything in this prefix. And furthermore, everything in between needs to be smaller than, less than or equal to 5. So anything in between cannot be a closer maximum. The first maximum needs to be 6. So I'll put some values here, 2, 4, 1. So this will be an example of a valid array. But if, for example, this 1 was actually a 7, that would be invalid because 7 is closer. It is closer from the left to the left, and it's also greater than this entire prefix. So that would not be a valid sequence. And so now we are simply asked to count. Now we are asked to just count the total number of valid sequences. And since this number could be very large, we are asked to compute this modulo 10 to the 9 plus 7. All right, so that is the premise of the second problem. Now let's talk about how we can approach solving this. So if you took the silver version of this contest, you've actually already seen a variant of this problem because this problem, the same setup was given to you in the silver contest, except the difference is that there they didn't ask you to count it; they just asked you to construct the lexicographically smallest sequence that works. But some similar preliminary analysis can be done to understand what sequences are valid. So let's first analyze like what conditions or what constraints need to hold for a valid sequence to exist. So I think the first observation, or this is not really an observation, but just the formulation that makes the problem like much cleaner to analyze is these A, comma H constraints can be viewed as intervals. Intervals from A plus 1 up to H. And so what this is saying is that if you look at it that way, then basically what this is saying is that everything in the prefix from 1 through A needs to be smaller than H, and also the maximum the maximum needs to be at position of the entire interval from A to H needs to be at position H. So this needs to be the maximum of the interval, the strict maximum. So there are multiple maximums, then that is not allowed because the first maximum needs to be at position H. So that's another formulation of this, is looking at this in terms of intervals. Now, why is looking at intervals helpful? Well, now we can analyze some particular cases of intervals. So let's say we have some situation like one interval is here. Let's say we have a situation where one interval is here and the other interval is here. Is this possible? Well, let's suppose that the value here is well, let's say the value here was 1. And the value here was also 1. So this needs to be the first position that is strictly greater than anything inside this prefix. So this could be something that's 2, for example, and that would work. That would satisfy this interval. But now that also means that the first position that is greater than or equal to this prefix, or sorry, that also means that the first position that's greater than this prefix is also this position right here, because this is 2, and not here, which is what we want. And so the only way this is satisfiable is if this is less than or equal to this. So this has to be 1. But if this is 1, then this is not the first position that is greater than this prefix for this interval. So we kind of arrive at a contradiction here. Like when two intervals are intersecting, or when one interval is nested within the other, it is never possible to have a satisfying sequence. So these types of cases are just simply not possible. So if we have some sort of like that's the case, we immediately know there are no sequences that exist. It's 0. What about intersecting intervals? Let's say the interval was intersecting. So one interval is here, another interval is here. Then let's try to satisfy this. So let's say this is a 1, and this has to be a 2. And now let's suppose that this is a well, what happens if we make this like a 2? If we make this a 2, then this would actually be the first position that is greater than this prefix. So that's not allowed. So this can't be a 2. This has to be like something smaller, like a 1. But if this is a 1, then the first position that is greater than this prefix is right here, and not all the way back here. So again, we have a contradiction. If two intervals are nested, it is also just not possible. It's also just not possible to build something that works if we have if we have two intervals that are intersecting. And so actually, the only cases where we can have a valid sequence are really simple. The only cases where we can have a valid sequence are when the intervals are completely disjoint. This is the only case where the answer was not 0, when there actually can exist a valid sequence. Because then for this one, you can do something like this is 1, and this is 2, and this one will also be 1, and this one we make it a 3, this one 1, make it a 4, right? And you get the idea, right? So like this is like the, or I mean, you can also have like something like this is also allowed. So they don't necessarily, so when I say that this joint also includes like it can be like right next to each other. So you can also have some situation like this. So that's 4, and then the 4 makes a 5 to make it satisfied. Yeah, so this is these types of cases where we have disjoint intervals. This is the only possible case where the answer is not 0. So from now on, we can just assume that we have just disjoint intervals. And when the intervals are disjoint, it is much easier to count the number of possible sequences. So I'm going to now have everyone consider the following dynamic programming approach. So we have these intervals that are disjoint. And let's say dynamic programming of I and J denotes that we are currently up to position I, and yeah, we are currently up to position I, and our prefix maximum is J. Now this would be O of n times c states if you just did like the exact position, but O of n times c is not allowed because n is way too large. N is up to 10 to the 9. So it needs to be O of q times c instead. O of q times c states. And the way we get to q is just like we only care about the relevant I positions. We only care about the ones that are endpoints of intervals. So specifically, we only care if we are either like here, the right endpoint of an interval, or here, like one before the left endpoint of an interval. Okay, now let's look at the transitions. So the transitions, what do they look like? Well, if it's going from like a right endpoint of an interval to here, then it really doesn't matter what's like in between. We can figure it out later. But let's suppose that we're going from like here to here. So we're going from the because these are disjoint intervals. So the only possibility is we're going from some left endpoint to some right endpoint, or from some right endpoint to another left endpoint. And so let's say we're in this case, we're going from the right one before the left endpoint of an interval to its right endpoint. And so that means, let's say we're going from dynamic programming of ij to the right endpoint, which is going to be dynamic programming of some new index k, and I'll say some j prime, some new prefix maximum. Well, what is the situation here? Well, the current prefix maximum is j. We have this interval. We need this to be strictly greater than j, and we need everything in between to be less than or equal to j, right? And so the transition is that to get to this new dynamic programming of k, j prime, which is k is really just like there's only a singular k, it's just the next relevant position. We need to multiply this. This needs to like basically plus equal dynamic programming. We transition from ij, but multiplied by the coefficient. Well, what is the coefficient? Basically we have any of these values in between can be anything less than equal to j. So there are j possibilities for each. The total number of them are like is like k minus I. Yeah, I think k minus I minus 1. And then k itself has to be set equal to j prime, which is greater than j. So our transition looks something like this. Now we just compute this naively. This is O of q times c squared, right? Because for each state, we iterate over all possible j prime to the next for the next prefix maximum that we can possibly transition to. That's too slow because c is up to 10 to the q. For some reminders, q is up to 100, but c is up to 10 to the 4. 10 to the 4 squared is 10 to the 8 times to the 100. That's 10 to the 10. That's too much. But we can speed this up from O of q c squared is just q times c with prefix sums. And the trick or the observation is that this multiplied factor, this j times j to the power k minus I minus 1, this is only dependent on the state we transition from. It has nothing to do with j prime. So instead, we just compute prefix sums on dp of ij multiplied by j to the power k minus I minus 1 for the previous layer, and then just use prefix sums to compute all of the new dp states really, really efficiently, just by adding all the previous j less than equal to j prime with their appropriate factors multiplied on. And so this speeds it up just from O of qc squared to just O of q times c. It might be q times c times the extra log factor or something, because when you pre-compute this, you need to use binary exponentiation to compute j to the power of k minus I minus 1 efficiently, where this exponent can be up to n. So you might need an extra log factor to compute the modular inverse quickly, or not modular inverse, but to compute the j to the power k minus I minus 1 efficiently. But that's still fine. Yeah. And so now we finally have a fast enough solution. So to recap, the keys to solving this problem was observing that the intervals have to be disjoint, and then after that, writing some sort of dynamic programming to compute this number of sequences where the intervals are disjoint, and then using prefix sums to speed up the dynamic programming transition. All right, so are there any questions on this problem? Okay. I got one more problem then. Let's quickly cover that. So the last problem, problem 3, there was nap sort. So problem 3, nap sort. This one was this one is a funny one. So the setup for this problem is we were trying to sort an array. We want to sort an array of n up to 2 times 10 to the 5 integers. But of course, this is not just a typical sorting problem. There's some weird sorting mechanism to do this. The way it is that there are two groups. There's Bessie, and there are all of Bessie's helpers. And so what happens is Bessie, she will initially pick a pile of integers. She will pick some integers from the array, and she will sort them themselves. So if Bessie picks k integers, then the first one, then the way that her sorting algorithm works, that she's going to take the minimum element each time and push it to the back of a new list. So the first one, she's going to take a k time to fix the first one. She's going to take k minus 1 time to fix the second one. She's going to take k minus 2 times to fix the third time, the third element, and so on and so forth, right? So in total, she's going to take k times k plus 1 over 2 time to sort like her portion of the array. Okay, and what about the helpers? So the helpers are going to have some leftover elements like a1, a2, up to like a of n minus k, because the helper is going to have n minus k elements. And what the helpers are going to do is they're going to take each element and literally have them sleep by like their value. So this is going to sleep for a1 seconds, it's going to sleep for a2 seconds, and sleep for n minus k seconds. And then once they're done sleeping, they push this array to the end of the list. They just push it to the end of the list. They push to the end of the list after a1 seconds. They push to the end of the list after a2 seconds. They push to the end of the list after a minus k seconds. And so now we want to know, well, first off, we need to make sure this is sorting it properly, because there are some cases where the helpers might push their elements too early. Like they push it before Bessie would push her elements, and then the array is no longer sorted. So we need to make sure this is actually properly sorted. But the second thing is so now we're oh, and also like in case of a tie, if like two things happen at the same time, like Bessie tries to push an element from her sequence, and one of the helpers tries to push like a sleeping element, then Bessie takes priority. And we want to know what is the minimum possible time to sort the array under these conditions. And the sorting is like the minimum possible time is like we get to choose like which how many elements Bessie takes, which ones she chooses, etc. And we want the minimum possible time to sort it. Okay, so how can we approach this problem? Well, at a high level, let's suppose that the maximum among all the helpers. Let's consider the maximum among all the helpers of like their A elements. So this is going to be an upper bound of how long it takes, right? Because the maximum value needs to wait for that amount of time. But then also Bessie's part takes k times k plus 1 choose 2 time to sort. So the answer, basically, if the array is properly sorted, then the amount of time it will take is the maximum of like all the array elements the helpers took, and the how much time it took for Bessie to sort her portion. And this kind of motivates fixing the maximum among the helpers. So let's say we sort all the AI. I'm going to draw some array elements here. Let's suppose we sort some all the AI, and now let's suppose that the first one that sleeps, or from the back, the last one that sleeps is this element. So that means that Bessie is going to take all of these into her array. So this is the maximum AI that we have enumerated. Then we basically want to find, among this portion, we want to find the minimum amount of elements that Bessie can take. Let's say the minimum B, such that Bessie takes B from this prefix and the array is correctly sorted. Okay, so this is actually kind of interesting now. So essentially, we have the subproblem of like, well, first of all, let's consider loosening our conditions. Does there even exist a valid B such that Bessie can take B elements from the prefix and then the whole thing is properly sorted? Does that B even exist? And it turns out that you can always prove that it exists. So let's consider the following subproblem. I'm going to give you a subproblem. Let's say we fix K, like how many elements that Bessie takes, and we have n elements where n is greater than or equal to K. Then if we fix K, this basically partitions the array to like K plus 1 intervals, where let's say these elements are strictly less than K, these elements are greater than or equal to K, but they're less than K plus K minus 1, which is equal to 2K minus 1. So basically the time it takes before the second elements from Bessie is put into the array. Let's say these elements are all greater than or equal to 2K minus 1, but less than 3 times K minus 3. So like K plus K minus 1 plus K minus 2. Let's say this interval is here. So let's say there are no elements that are greater than or equal to 3K minus 3 and less than 4K minus 6. And then finally, these elements are going to be greater than or equal to 4K minus 6, right? So in this case, K was equal to 4, and we had 5 intervals partitioning based on whether they must come before or after each of the K elements that Bessie will be putting into the array. Then the question is it possible for Bessie to pick 4 elements so that the remaining elements are correctly partitioned? So one way that works is that Bessie picks this element. One way that works is that Bessie picks this element, this element, this element, and this element. Because now everything to the left of 1 is less than K. Everything in between 1 and 2 is greater than or equal to K, less than 2K minus 1. Everything in between 2 and 3 is greater than or equal to 2K minus 1, but less than 3K minus 3. Nothing in between here, and everything greater than 4, nothing exists either. Okay, so I mean, this kind of passes the eye test. We want to prove that in general this is always possible, and so the proof goes something like this. We have these intervals. Let's instead consider the slots in between the intervals. We're going to draw kind of these kind of like pairs of slots. So redraw this diagram. And what we want to do is basically want to match. We basically want to match array elements to slots so that the remaining elements are partitioned correctly. Partitioned correctly meaning that the stuff that was not picked are on the correct side of the slots they should be in. So like an example of a wrong partition was if we did something like this. This is wrong because this element was supposed to be to the left of the second slot, but it's actually to the right because it's to the right of the second element we pick. And so now we will just do the following algorithm. We're going to start from the prefix and we're going to consider the first point. Yeah, we're just going to start from the beginning. And we're going to consider the first point, the first position where let's see. Yeah, so we consider the first position where there are more array elements than at least as many array elements as slots. And then we're just gonna go ahead and assign them. And then we kind of have the this recurring. Or actually, let's do it this way. So we're gonna consider the first position where there are an equal number of array elements and slots. And that if that doesn't exist, if that doesn't exist, then we just kind of assign them like this and it works out. Right? But suppose that doesn't, like that. So we can just assign it like this and it would work out. But let me give a better example. Let me give a test case where it's not so trivial to just like figure out how to assign the things. So you see how like 3 slots here, and then 1 slot here, 1 slot here, 2 slots here. The only condition is that the number of slots should not exceed the number of total array elements. Okay, let's do this. So for here, let's consider the first prefix where we have and we have at least as many array elements as slots. And then we will assign all the array elements to the slots, and then consider this like recursive subproblem. So this is going to be a proof by induction. As long as the number of array elements remains greater than or equal to the number of slots, this is we just apply like an induction hypothesis and like go down to like a smaller case. So here we have 3 slots and we have at least 3 array elements. We assign all of them and we move to this subproblem. Now we have this is the first prefix where there are as many slots as array elements. So we just assign it here. And now we're in this situation. Now the first prefix, so this is true, is here. So we just assign it here. And then finally we have this. We assign it here. And indeed, all the array elements are partitioned correctly in this particular example. So the only ones that were not taken were these ones, and they are to the right of the final slot. And so we can always apply it out. We can always apply that out. So we can prove now that like it doesn't matter as long as there are n elements and Bessie is taking k less than or equal to n elements. There's always some valid like set of k elements she can pick so that the array is properly sorted. Okay, so why is that relevant? Let's go back to what we were originally trying to do, which is originally we were trying to fix. We had a bunch of array elements in a row, and we were fixing that the maximum elements that is not taken by Bessie. So this is this is sleep. This is the maximum element that sleeps. And then Bessie takes these elements. And now for here, because we know that as long as k is less than or equal to 5, it is always possible to pick elements to properly partition this. So all we have to worry about is if this element is properly partitioned. So we just need the maximum or the minimum k such that let's say this is k1, there are k2 elements on this side. The minimum k1 element such that it should be k1 plus k1 minus, or wait, such that the sum of k1 plus k2 plus k1 plus k2 minus 1 plus dot 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 plus up to k2 plus 1. So basically, the amount of time it takes to sort for Bessie to process all these elements in the front is less than this array element. Let's call this A. This needs to be less than A, so that the this skip element is pushed back far enough. And then A needs to be less than or equal to this same sum. So k1 plus k2 plus k1 plus k2 minus 1 plus up to k2 plus 1 plus k2. And if this is satisfied, if this inequality is satisfied, then by our proof earlier, we're going to be able to pick valid elements to fix the rest of this stuff. We delay this array element sufficiently far back, and then these elements are all picked by Bessie. No issue there. And so therefore, this is a valid sorting condition. And so once we find the minimum k for which this is true, then our answer for this particular for this particular choice would be the maximum of A and k1 plus k2, that same formula, right? k1 plus k2 times k plus 1 times k1 plus k2 divided by 2. And then we just try this over all possible k2. So over all possible choices of the maximum, we try this. So in total, there are n different maximums that we can fix. And for this, doing all of this, you can either directly solve for it, you can either directly solve for this, because it should be like some sort of quadratic, or you can just do binary search if you don't want to work out the details. The binary search works in, I say, log of n as well. So this is an O of n log n solution. Yeah, so let's just quickly summarize what we did. Basically, we are fixing the maximum elements that is given to a helper that sleeps. The Bessie takes all the elements prior, and then we just need to figure out the minimum number of elements Bessie needs to take from here, the prefix, so that this entire thing is sorted validly. And it turns out all we need to do is check this inequality, because we don't need to worry about picking the wrong elements that this prefix part is not sorted properly. We just proved that it's always possible to pick prefix elements to sort the prefix properly. So we just need to check this inequality, and the code ends up being relatively short. And it's O of n log n. Okay, now so we have a lengthy explanation, but are there any questions? Okay, let's return to the slides then. Give me 1 second. Let me open the slides again. Okay, so we are almost out of time, but yeah. Yeah, hopefully everyone can see the slides. So yeah, basically, these are kind of the knowledge points I would say you roughly need to solve these problems. Of course, like it's not just binary search, not just greedy, but certainly having good foundations in those topics would be are necessary to be able to solve approach these problems. And so we have listed the relevant XPM courses that correspond to each of these topics. And yeah, we also have the XCamp USACO report card that you can get if you want to register for that. So you just visit the website and claim your USACO report. And yeah, are there any questions? I know we're almost out of time, but I can quickly answer if there are any remaining questions. So apologies for technical difficulties today, but we got to the end eventually. Yeah, okay. I guess there are no questions. Is the session's over?
Yes,
Yes, how good.
Dorian, maybe you can ask questions because
Mm.
it's pretty good time to discuss with our coach and teachers.
It's okay if you don't have questions now. Yeah, I think I'll see you like 2 days from now. Okay. All right. Yeah. Thanks for coming, everyone. Yeah.
Yeah, thanks. Thanks for joining our live solution. See you next month. Max.
Yeah. Yeah.